For this project, Oliver and I were tasked with creating an orbit simulation in Python based on Newton's law of universal gravitation, and determining whether our orbit conforms to Kepler's laws, among other things we'll get into later. We first created individual spreadsheets to simulate Earth's orbit, deriving its x and y positions from Newton's law of universal gravitation. We made each of the first boxes here refer to the initial conditions, then every box below referred to the last box. Using all x and y positions, we created this graph of Earth's orbit. To check whether our sheet was accurately simulating the orbit, we found the time it takes for the orbit to return to its original x position. This resulted in a period of 368.06 days, a value quite close to the Earth's actual period of 365.256 days.
Now that we'd confirmed that we'd successfully simulated an orbit with the spreadsheet, our next step was to simulate this orbit in Python using matplotlib for the visuals. Now, the easiest way to do this would be to directly copy and paste the math from our spreadsheet into our Python code and change a couple variable names. However, this has a couple problems. First, the satellite always orbits around 0, 0. And second, the sim can only model one object. In order to simulate more complex orbits, we changed the logic a bit. Firstly, each planet is stored independently in its own object. Secondly, when you're calculating the movement of an object, you can input multiple hosts. Then, the function calculates the acceleration the body feels from each host independently, using pretty much the same math as the spreadsheet, except the function calculates the distance the satellite is from the host and uses that to calculate the force instead of assuming that it starts at 0, 0. As it calculates the acceleration from each host, it adds them together to get a total acceleration. What this means in practice is that there's no real difference between satellites and hosts anymore, except that the hosts have more mass and are not impacted by the gravity of the satellite, unless you want them to be. Now, the reason this is a much better way of doing things is because it means that the simulation can now account for moving hosts and more complex orbits, where both objects are moving and there is no clear host. Here is an orbit of a two-star system similar to the Alpha Centauri star system, where both stars are orbiting around their common center of mass, or barycenter. Why stop at 2 stars, though? Here's a stable 3-star system. This system is following a similar type of orbit to the real Solaris system, aka the North Star, except all 3 stars have the same mass and the distances are much smaller.
Now we had to prove that our simulation followed Kepler's laws of planetary motion, so we chose to analyze laws 1 and 3. Kepler's first law states that all orbiting objects move in elliptical orbits around their host, with the host situated at one of the two foci of the orbit's ellipse. So to prove that our simulation's orbit was an ellipse, we found the vertices and co-vertices of the orbit by printing the x and y coordinates of the object. By finding the object's x position where its x position went from decreasing to increasing, we found a vertex, and by doing the same with the y position, we found a co-vertex.
We then used the glorious program that is Desmos to prove the orbit's elliptical nature. Now, we plugged in the vertex and covertex for A and B respectively into the equation for an ellipse that we have here. Now, we then found where the middle of the ellipse should be, which is C here, and we plugged that into the equation using this equation, root a squared minus b squared. And using this strategy, we can see that the focus is at 0, 0 here, proving that the host is at the focus of the ellipse, since our simulation places the star at 0, 0.
Kepler's third law states that the square of a planet's orbital period is proportional to the cube of its semi-major axis. To prove our simulation follows this law, we continuously printed the change in time and x position of the planet, and found the time it takes for the planet to return to its original x position.
Then we found the semi-major axis of our Desmos ellipse by finding the distance between the perihelion, which is the closest point between the orbit and the focus or the host, which is just a vertex, and the center of the ellipse, which is the intersection point between the minor axis and the major axis.
By using Kepler's formula, t being period and a being length of semi-major axis, we had very similar numbers on both sides of the equation, showing that our simulation followed this law.
Trojan asteroids are asteroids which are caught in locations in space called Lagrange points. Lagrange points are formed between two bodies of different sizes, such as the Earth and the Sun, where a satellite can sit in one of these places and have its position stay constant relative to the other two objects. Trojan asteroids specifically exist on either the L4 or L5 Lagrange points, which are located 60 degrees ahead of or behind an orbiting planet. To see if our simulation could model this, we first calculated the initial positions of the Lagrange points of Earth using Desmos. Then, we did some vector math to rotate the Earth's initial velocity to get a rough estimate of the velocity of the asteroid at that point. This velocity is not exactly right due to the Earth's eccentricity. However, objects near Lagrange points tend to stay near them due to the Coriolis force, so there's some margin of error. We took these initial parameters and plugged them into our simulation. Importantly, where the objects were being affected by the gravity of both the Sun and the Earth. There, we saw the two satellites sitting in a stable orbit, stationary to the Sun and Earth.